All right. Good morning, guys. Thanks for coming and filling up the classroom a little bit. Let me see. I want to first show you some studies I happened to find. Yeah, this is pretty cool. For example, all right, so this is not the most accessible content necessarily, but this one I don't think is too bad. Let me see. Yeah, this is all about the 15-minute city. Have you guys heard about the idea of a 15-minute city? Yep. Okay. Very walkable, everything's kind of like within reach. I just wanted to find a study that showed a certain application of stuff we're doing. This one actually shows, for example, they do is this the one? Yeah. Correlation analysis, right? That's what we just got into. Correlation analysis, they found out that, blah, 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 blah. Wait, I just saw it. There we go. Statistics on population density are presented and seem to be strongly positively correlated with the percentage of the population living in neighborhoods meeting the 15-minute city. Okay, so, I mean, just another example, and I have several up here. I'm just going to go through each of them. Another example of how what we're doing is immediately, you can see it in studies that are being done now, studies that have been done. So I always like to point out to students, especially statistics is the most immediate. You can go see a journal article, you can see a study, an analysis, and you can see exactly what you're learning in it. You with me? Now, the content that the analysis is working on is very often out of reach. But if anybody's going to go into nursing, once you get far enough in nursing, you couple that with your statistics knowledge, and you can interpret a journal article about some nursing procedure or something. Yes. So it depends on how far you go down certain fields. If you couple that with statistics knowledge, you can then read and feel confident about what the hell they're trying to tell you. Does that make any sense? Yep. So statistics goes with everything in the universe, because what can you study? Everything in the universe. So no matter what field you're going to go into, it's just good to know how to interpret statistics, because someone somewhere is going to do a study related to your field. Does that make sense? And you're all here, so it's like, it's weird that I sound like I'm trying to get you to sign up for stats. You're like, we're here, Jeff. But just to affirm that what you're learning is going to be useful. All right. And just, here's a bunch of confidence intervals. Do you see that? 95% confidence intervals just running all over the damn place, yes? I should go back here and show you. Look at the where'd it go? Darn it, Jeff, you lost it. You lost it. You lost it so long. Here, down here, look. They describe what statistically significant is down at the bottom. Or they tell me it's like little asterisks, right? When the p-value is less than something else, yes? So that's kind of like, if I'm looking at this, I can interpret for myself if it's strong enough evidence or not, just like I told you guys in class. They're never going to have an alpha. They're just going to report a p-value. And then we have to evaluate that to see if it's enough evidence. Does anyone have questions about homework or general things? Yes. Okay. Here in a bit. I forgot my glasses, but okay. So we just started the lecture, so I want to focus on general questions from homework. You can ask me that here in a little bit, okay? Well, I got my glasses now, but do you guys have any general questions from homework? Everybody got their stuff back, right? Oliver? Oliver. So if you weren't here last night, I need to see if I got the handouts from last time. Yeah. Oh, for that, but it should say contains. Because the whole idea is our confidence interval should catch or contain the real. Okay. All right, guys. So we got into, or actually we got into linear correlation and regression last time. Yes? What were the two main things that, given a set of two variables, what were the two things we wanted to be able to calculate? What does that translate to? The line of best fit is kind of like a graphical mean. Yes? It averages out the position of all the points. So it's not the mean, but it's the thing that acts like the mean. The line of best fit. And of course, in just pure data earlier in the semester, we wanted to know the mean, and we also wanted to know the correlation coefficient. I'm sorry. Earlier in this semester, we wanted to know the mean and the standard deviation. The two analogs to those for a set of two variables is the line of best fit, that's a visual average of the data points, and the R value is a measure of how far from that middle line they get. What is the standard deviation in the earlier part of the semester is a measure of how far from the middle the data points got, correct? So that's that's exactly what it is. Every time I give you another way to get information, to get data, I want to know in that situation, how do I get the mean? How do I get the standard deviation? So with sets of two data points, two variables, the mean becomes the line of best fit, and the distance away from that mean becomes the R value, right? The correlation coefficient. How do you guys? So if I had every point line up perfectly on my line, that's like every data point being equal to the average. The standard deviation should be 0. In this case, we made it so that my number that represents the spread also tells me if it's a positive or negative slope. Yes? So in our case, if all the data points line up perfectly on a line, that would be R equals 1 for a positive slope, R equals negative 1 for a negative slope. So just to really make this as clear as possible, I love the analogy because it's exactly true. The mean becomes the line of best fit, standard deviation becomes R. The values of R are not the same as for standard deviation. What does R equals 0 actually mean?
Well, the data points are all over the place.
They're all over the damn place, yes? So, but what does standard deviation equals 0 mean? They're all perfectly the average, yes? So it's kind of like the opposite in a way. But we just created the formula to do that. So that if R was 1, we know it's perfectly positively correlated. If R is negative, it's perfectly negative. And the minute I get a little bit away from those, the data points start to get away from the line. If the data points really get far away from the line, then you're getting closer to 0. All right, looks like you guys are okay. All right, I like it. So, did I bring, I did. Does anyone need the handout from last time? Anybody? Yes. You missed my whole talk about drinking beer and taking tests. Drinking beer. Very often in college you drink beer because you take tests, not to take tests. Or, some other beverage.
Challenge accepted.
Not a challenge. Not a challenge to the students, okay. I'm gonna make sure that's picked up by the mic.
I got all my notes.
Huh?
Like a madman, they scripted so much stuff. Like, I made a laugh.
The next step is to have little reds going, put them all up on your bedroom wall, connected with red thread.
Is that how you write it?
Yes,
Is that
well,
what
that's
you
the
write?
standard, like, madman in his room trying to make connections. Okay,
Charlie.
what I want to do first is I want to have you guys do an example correlation problem. Yes.
Line of best fit is called what again? Correlation.
No, the line of best fit is called the line of best fit. That is its official name.
Oh.
It is also called the least squares line.
Oh.
That's not as important, but just to let you know. The
The
correlation coefficient is the little letter R.
Oh,
Yeah, that's the strength of the correlation.
thank you.
You're welcome. It's like a whole job or something. Okay. So I need to figure out, let me do this. Does anyone need to borrow a calculator? We're gonna desperately need those. This is the one section, the one chapter where we basically do everything in the calculator for the most part. No CGs.
There's so much to do.
I believe you. So let's do a little quick example together, and then I'm gonna unleash you guys on. Oh my God! Somebody. Okay. So let's do this. Let me get away from all that freaky data. Let's say I've got these variables. You can do it, Jeff. Can somebody, so you guys all have that copy down? Can somebody tell me, I got two things I want to kind of get from you for this data. Number one is, can anyone predict if the R is going to be negative or positive?
Positive.
Okay. What does R represent? When is it negative? If the slope is negative. So when one variable increases, if the other variable decreases, that's a negative correlation, which is exactly a negative slope. So as x gets bigger, what does y do? Getting smaller. So I know ahead of time this R is going to be negative. Do you guys see how, again, everything we're doing right now is not really necessary, but it's kind of nice to know ahead of time what to expect. So if you see something completely off, you're like, I put something in my calculator wrong. Do you guys see how this kind of goes pretty well with how this is changing? Like this went up by 3, this went down by 8, this went up by 2, this went down by 4, a little bit less. This went up by 4, this went down by 6, a little bit more. It seems to be sort of changing at the same kind of pace. So I would predict, and this is why I try to create it, I would predict R is going to be decently close to -1. Because there's none of them that kind of like go against the pattern. If I made this 43, do you see how that would go against the pattern? That would be more real life, but it would go against the pattern. The trend would still be negative. R would still be negative. It just wouldn't be as close to -1 because now you have somebody that's far away from the line. It doesn't follow what the other ones seem to be doing. And of course, that's pretty good real life, yes? So in real life, we can talk about trends. We almost never get data points that line up close to perfect. When that happens, we're like, we did something wrong. All right, so let's all put this. Everybody can do this first step, even if you weren't here last time. Just put these two variables, clear these list 1 and clear list 2, and just put X is in list 1, Y is in list 2. Jeff, what did you just do? There you go, buddy. I agree, bless you. Okay, so you'll get this here. Hey, Kels, do you need a calculator?
Yeah.
Thank you.
Oh. Oh, yeah, go ahead. Did you get one of these? From last time? Okay. That's basically what we're doing right now.
Okay.
All right, guys, can somebody who was here last time, and if I said yesterday, you know what I mean. Where do I go from here to make the data points show up on the screen, to have the calculator graph the data points.
Stat, calc, and then, go forward, and then right.
Oh, that would be if I wanted to calculate the two things, the median and the standard deviation, which in this case is the line of best fit and the R, the correlation coefficient, right? I just want the scatter plot, I just want the dots.
Oh, then,
All right, so if I hit graph, so real quick, if you weren't here yesterday, or if you just borrowed a calculator, let's all make sure, hit second y equals. So you see above y equals it says stat plot? And it kind of makes sense, I'm trying to plot some statistics. So stat plot sounds like a good place to go. See,
Or you said y equals?
hit second y equals. You right
Right.
above,
oh yeah, and.
I did, because it's right above y equals.
Do we get to pick any plot?
You could, as long as one of them's turned on and set correctly. So I'm gonna do the first one. Most of you guys, it should be turned on, right? Because it's from last time.
Yeah.
I'm gonna go in, I'm gonna turn on my plot 1. I'm gonna make sure that I've selected scatter plot here. If you weren't here last time, look at all the stuff it could have done for you. Sorry.
This is it.
It's a little it's a little, what do you call it?
Jesus.
No. Public service announcement. Read your manuals, kids. You never know what it can do for you. Is everybody with me?
Yeah.
Let me know if you're not in this screen right now. It's okay if you're not. Don't be ashamed. Okay. Turn it on. Just hit enter when you're hovering over on. Make sure you have the scatter plot picked. Make sure L1 is your X's, L2 is your Y's. This little symbol is just what's going to show up on each data point. So obviously, like I said, I always pick a square. And I'll go with blue, sure. And I'll also just decide randomly to get out of there. Okay. So are you with me? Yeah, now, if you hit graph now, shit. What did I forget? Zoom? 9. So calculator. That calculator is dumb. In fact, it doesn't even register enough to be called dumb. It's a piece of plastic with some metal inside. What do you do? It's just going to show you this window until we tell it to change it. So if I hit zoom, I can then zoom in, zoom out, all this kind of weird shit. But obviously, I want to tell it, please calculator, zoom in on my statistics. So if I just hit the number 9, I get that. So let me know if you didn't get to this. If that's not showing up for you right now, let me know. Why is that very important, guys? What's going to happen on the day of the final?
Yeah, we have to show you it though.
Yeah, you're going to have to show me this. Okay. All right. Does that line up with what? No pun intended. Sorry. Does that line up with what we were saying earlier? It's a negative slope. It's pretty close to -1, I would say. Especially now, you can tell that's almost perfectly straight. That's
Yeah.
oh. Okay, so you got it turned on. You got that. Yes. And now you just hit zoom. Up here. And then the 9th option should be zoom stat.
I was looking for zoom.
I think it's the 9th option, right? Okay. There you go. Yeah. Now, this is not good enough to show me, but I just wanted to let you see it without a line on top of it or whatever. Now, somebody tell me, remind me, how did I calculate the two things I need?
Stats. Yeah, you go to stats and then line of right, whatever.
That's done before.
I'm not laughing at you, I'm laughing near you. Yeah, you go to stat, and then I want this to calculate a line of best fit, so it makes sense to use this guy. Ignore that guy. Right? Ignore that guy. I don't know why he's this. So we're going to use this guy. These are both the same, guys. 4 and 8 are both the same. It's just whatever the slope is here will be A, and whatever the slope is here will be B. Same numbers, same everything. Why does that exist? I don't know. And when I try to ask TI, they think I'm a spy from HP. So, what can I do? Okay. So everybody hit number 4 for LinReg. That's linear regression is the official name of this analysis. I explained why last time. Make sure it's L1. What is this currently for you, Jeff? Oh my God, somebody weird was using my calculator. So L1, L2, and then go down to calculate. Kabam. Oh, I got to do this too. Oh, this is perfect. Some of you guys might have the same issue. Did anyone get more information than what I got? What information did you get? R squared and R, yes. And that's good because all I got was the equivalent of the mean, the line of best fit. The stupid calculator didn't tell me R squared and R. It's not the calculator's fault. Does anyone else just get what I got? You got? Anybody else just get A and B? Or what's up?
It's this thing.
Yeah, exactly. Okay, so you and me are in the same boat. Everybody else thinks they're hot shit just because we don't have the right button push. So you ready? So if anybody else has just these showing up, do what I'm about to do with me. Hit second 0. You're never gonna have to do this again. On the day of the final or the day of the whatever, I can make sure your calculator is set correctly if you have to borrow one from you. If you have your own, you've already got it set. You don't have to ever change what we changed in here, okay? Are you with me? Okay. I want to go to the section of the alphabet, the D section of the alphabet. So do you see the letter D above this button here? The X to the -1 button? Just hit that and it will go to the D section.
Wait, how do we get here?
Huh?
How do we get here?
Second,
Oh, second 0. And then I hit this button that's got the D above it. So now I'm in the D section. And now if I just scroll down to diagnostic on, enter, enter. Very anticlimactic. Just says done. Hey. So now if I recalculate stat, calc, linreg, now I'll have what everybody else got. Oh, you're ahead. All right. Show off, whatever. Sorry, you're good. So, did it do what we predicted? What's our R value? Yeah, really close to -1. Even closer than I thought it would be, to be honest. But
On the quiz, are you gonna be asking for like what's R?
I'll tell you. On the,
I like this.
yeah, exactly.
Just
I'm
like
gonna
this.
ask basically those exact same questions. Yeah. How would you interpret R? What does it tell us?
It's not a strong correlation.
Yeah, what would be perfect negative correlation? -1 is perfect negative correlation. So this is freaking close as shit to perfect. Yeah. And it's not impressive because was the sample very big? Let me ask you guys this. This is gonna be tricky, right? If I have a sample of 2 points, R will always be what? If I have 2 points,
Only one.
doesn't a line go straight through them? Always? So as long as they're not right across from each other or something, if they're diagonal from each other, R will be 1 or -1 based on if it's got a positive. So if I have a sample of 2, R will always be 1. That's why the smaller the sample gets, the higher the level of evidence needed. If you have a sample of size 2, the evidence needed is beyond 100% because that's not enough evidence. I need at least one more data point to tell, where the line kind of seems to be. Our sample is very small, so it's not hard to get a very close to perfect R. Okay. So now, let me show you 2 things. First off, can everybody copy down the line of best fit? I'm gonna go kind of far out. I'm gonna go like this. Far out, Jeff. You're right.
It's my uncle.
Yeah, kids. It's bad to get ahead of you. No, you're fine. If you rounded it, you're fine. It's not that big of a deal, to be honest. You just don't want to make it -2. That's a little too big of a round. If I go to y equals, and I plug in negative, remember the negative button's down here. Negative 1.9855, and your x button is right here. Negative 1.9855x plus, where'd it go? 50.893. Now if I hit graph, it'll include the line of best fit, which looks like it's doing exactly its job, yes? Okay. So visually you can tell if your line of best fit's off. If you have an issue, you can just come up and show me. Normally it's just you left the decimal out or something. Okay. Is everybody, that's what you would have to come up and show me. Huh? Okay. It's not a bad idea. Okay. So what I want you guys to do. Oh, the other thing I want to show you. This is completely extra shit. You ready? I just want to point one thing out if anybody was curious about this. Did anybody notice, if you have one of the newer calculators, get this whole list of things, yes? Frequency list means the same thing it always has. If I had like a P of X list, like 10% of my data was this point, 25%, blah, blah, blah. Then I can tell it which list has that in it. We don't have a frequency list. We never will for this. But the next thing, look at this thing. This is complete extra icing. You got your cupcake with icing and you're like, can you put a little more icing on there? So everything I'm about to do, you never have to do ever. But you see, this sounds very interesting. Store regression equation. Store regression equation. Okay, so here's what I want to do. Now, again, just reminding us, you do not have to do this. Do you see where it says variables right here, vars?
Yeah.
If I go to variable, so look, see where I am? Store regression equation. Go to variables, go to y variables, function, y1, and then if you go to y equals, it put the whole damn equation in for you. You see how that's just freaking icing on top of icing? You never have to do what I just said, but just in case you were curious what that store reg ec meant, it'll store the equation for you. But weren't we able to just type the dumb thing in there anyway?
Yeah.
So who cares? Yes. Just in case. Okay. So I want you guys to. Here we go. By the way, after we do this review, we're gonna do our next chart. Yeah. Okay. Sorry. Our last chart, I should say. No more time for new charts. Yeah. Should be doing this. Totally, because the R was bodacious. Yes. Sure. Wow. By the way, the side that's got stuff about M&Ms, don't look at that side yet. It's something we haven't talked about yet. Not M&Ms, but process. You got one? I want one, two. So, this side we're gonna get to, look at this. Ooh, okay, stop looking at it. Okay. This side. I said group work, but I'm not gonna force you into groups, but if you wanna work with somebody else, feel free. I want you to do that number one. Don't worry about, well, you could do number two if you get done with one, that's fine. But don't worry about number three at all. Don't worry about that yet. Do number one. Let me know if you have technical issues, questions. If you just want to let me do this together now. All together now. Oh, by the way. Okay. let me officially announce the last quiz of the semester. And it's going to be on this linear regression stuff. That's what those words say. Will be next Tuesday.
Next Tuesday? This upcoming Tuesday?
Of course. Because then what's happening next Thursday? Review for the final. Because then what's happening the Tuesday after that? Yes. So, 2 weeks from today.
Yeah, it's fine.
No, I'm sorry. 2 weeks from Tuesday is our final. You with me?
Not this Tuesday.
Next Tuesday, we're going to have a quiz on regression. Chapter 12. Yes?
What's the last day?
Hold on. Next Thursday, so next Tuesday I will give you the practice final. Next Thursday will be review for the final. I'll have an answer key for the practice final. And the Tuesday after that is the final. Now this is not news to you because it's on the syllabus and it's on the homework sheet. Which is why I don't have it here, because I know all of you have it there. Yes?
Is it like a final, like every chapter we've done, or is it like the most recent chapter?
It is cumulative the way every math final is supposed to be. Okay. So is everything? Yay, Jeff, yay. How much time are you going to have to take the final?
The class.
Whole class, which is the same amount of time you have to take any test, correct?
Yes.
So how long can the final be?
As long as it's
Same as a regular test.
Yes, if I wasn't evil. No, I'm joking. It's going to be the same size as a regular test. So will I be able to put every single idea on it?
No.
Well, am I going to tell you exactly which ideas I'm going to put on it? No.
You know what? I don't even mind.
I do.
Well, good, because it doesn't matter if you did. Just to be really blunt. So I make the practice final is going to be a little bigger than the final is going to be. I'm going to have the answer key for that. We can all study together. Is everybody understanding what's going to happen the next 2 weeks? Yes? We're almost there, guys. I'm going to miss you guys, though, but we're almost there. All right, so coming back to this. Oh, I haven't even put this in here. Good job, Jeff. So everybody, just watch in awe as I do this.
Are we gonna do the back of this paper today?
Yes.
Yeah.
Stay with me now. Did you guys get the other questions answered on number 1? No? Yes? Okay, thank God. Okay. So let me see if I get the same thing you guys got, because I did that a little bit quickly. I get this. Okay, thank God. So I got 1.03x plus 61.87 roughly, and my R was 0.919. What does that tell me? Okay, good. It's a strong what correlation? Positive. What does it tell me about the line of best fit? There's 2 main things you can tell me.
Positive.
Okay, so it's got a positive slope. That's basically what the R tells me. Yes? R is close to 1. Yes. So I know that. What does that mean then?
Strong correlation.
Sure, but that's what we already said. Strong positive correlation. So what does it mean about my line in relationship to my data points? My data points should be close to the line. Yes? So one way you can answer that question, guys, which I'm going to ask you on the quiz and the final, is this R tells me the data points are tight or close to the line. Or you could say, you guys tell me, would you trust this line to make predictions?
Yes.
There you go, you could also say here, I would trust the line to make predictions.
So strong positive correlation and I would, because the data points are close to the line.
Because R is above 0.532.
Okay.
Even if I got 0.533 R, is that evidence of correlation? Is it strong correlation? Hell no. So if you got 0.533, you would say that's weak positive correlation, yes? Okay. How's everybody doing? Are you guys taking in? Are you picking up what I'm laying down? Taking in what I'm saying? Okay, yes.
So yeah, so it's just like the data points are just line, or that you could trust the.
Beautiful. So to answer this, either I'd say data points close to the line, or you could say I would trust the line to make a good prediction. Why did I good? Sure, Jeff. A good prediction. Okay. So how do I do part D? Because I just said I would trust it, and now I'm saying, okay, do it then. So predict the correct grade for someone who did 13 homework assignments. How would I do that?
We do the y ax plus b formula and then for x we do 13.
Kick ass. So we have our line of best fit. I would throw at 13. Why am I putting that in for x? Because that's what x means. So if I said, how much homework, somebody with a grade of 80, how much homework would you predict they did? You would put 80 in for y, yes?
Would you put 0.8 because
No.
it's 70%?
No, because we wrote these in as pure numbers, yes? So if you do that, what do you get?
75.28. I rounded to 75.3. Can I do that or should I do
Oops.
it?
Let me catch up to you.
Sorry.
Yeah, 75, I get 2.6. Oh, I rounded my stuff a little differently here, yeah?
Yeah, yeah.
So I got 75.26, you got 75.28?
2.8.
That's crazy. No, you probably rounded less than me, yes?
Yeah, I just
Okay.
kept it the same, but I went out with
That kicks so much ass. So does that mean if somebody does 13 homework assignments, they will get 75.26 or 75? No, but that's a prediction, yes? The actual outcome could be different. So why is the prediction not perfect? 2 reasons.
Oh, it's not perfectly one?
Good, R is not 1. Even if R was 1, another data point doesn't have to line up with the ones that were there already. Yes? But if R was 1, I would really, really feel good about our prediction. But I would understand it's still just an approximation. It may. Yes? So, there's good stuff happening, but I can't let it. This equation, yes, was built off of these variables, yes?
Yeah.
This is like the x's, correct? Like an xy table. So what does x represent? What does x represent based on what I just said? What is, these are the x's, these are the y's. XY table. So what does x represent? Yes, the homework's attempted, yes? So this one says, what if somebody did 13 homework assignments? Well, where do I put 13? You just told me. In the x, because that's what x represents. So x is the spot where I would put the number of homeworks if I knew it. I just put an x, this is the entirety of algebra, by the way. I just put the x in the spot where I don't know what it is. So a future person could go, oh, I know it's 13, I'm gonna put it there instead of x. That's algebra. Okay. How do you guys, is that cool? I also showed you how to do it in the calculator, but you can do it that way if you want to. Yes.
This on.
X, Y. X is his homeworks. 13 homeworks, put 13 in for X.
Oh.
Yep. That's what the line does. Now, guys, real quick. If R had been 0.533, is that evidence of correlation? Yes. Is it strong correlation? No. I would still trust it to make predictions, but I would understand the prediction is probably going to be weak, not a very good estimate, right? If R was 0.531, not evidence for correlation, would I use the line of best fit? Nope, because then I can't trust it at all. It's got a very knife's edge again, yes? What do I do then? If I don't find correlation, what do I tell somebody? I would just tell them the average grade. Anytime I don't know specifically, I just have to tell somebody the average. Yes? You would? Yes. Yeah, so I'm going to give this number to you. There's a whole chart based on sample size. The bigger the sample gets, the lower this requirement gets. It should be easier to show evidence if I get a bigger sample. Does that make sense? The smaller the sample, the higher that goes. It gets harder to show evidence based on a small sample, which it should be. I'm going to give you that number. I'm not going to give you the table and make you look it up. Yeah. I'm just going to give it to you. I can make this whole thing into a hypothesis test. And I didn't see a reason to, because it literally is just, do you beat this, and then it's correlation. Yeah.
So, now you said if you can't find a correlation, you use your mean for, like, if you just predict the average, what was the average mean? How would you find it?
Oh, just average the grades.
So, like, add them all, divide by 2.
Add them all, divide by
Oh, how many?
14 or whatever it was. Yeah. Yeah.
Sorry.
So divide by 2, because then you're like, I think you'll make about a 730. Oh, wow, dude, that's gonna totally lift my GPA. All right. Sorry, I'm feeling a little sassy this morning, apparently. So, yes.
I'm sorry. One more time. So if you don't find a correlation, you would add up the current grades and then divide it by 100.
Yes. So if somebody says, what if I do 13 homeworks? All right, guys, listen. In general, what's my best guess for a value from a set of data? The average of the data, yes? If I knew the average age of gross fund students was 24 and I randomly pick a student, what's your best guess for their age? 24. So what this kind of study does is it says, if I find enough evidence, I can then use this as a refinement. It gets a better estimate than just giving somebody the average. Because I have more information now. So if somebody comes to me and I own a business and like, how much money could I make working at your place? I would tell them the average salary. If they come to me and they say, I have this skill, and I've worked this many years in this and that, now I have more information. Now I can give them a more detailed idea of the salary they make. You guys with me? Yeah. So that's all this is doing is, without this kind of information, our best guess is the average. With this information, I can refine my best guess using this tool. It's the same thing in real life. The more information you have, the better you can kind of tell somebody what's going to happen. Yes. Am I going to fail the test? I don't know. Did you study? What are you doing? Did you drink beer last night? I don't know. What about number 2? Can you guys? What would a correlation coefficient of -1 mean?
That they're very close together going negative. They're like in a
Yeah.
perfect line going negative.
And yes.
For number 3, so that's all we just have to calculate it, but not
Well, this is it. Yeah. That's what I would predict for somebody. Does that mean they have to make a 75? No. But that's our best prediction. Okay. So correlation coefficient of R equals -1 means they line up perfectly in a downward slope. So therefore, drawing an example should be easy, yes? The best way to do it, by the way, instead of trying to draw points, draw a line first and then put points on the line. And then you can't go wrong. Even if your line's all wavy, they still line up perfectly on the line. Yes?
So how do you get like
The axes?
that's, I think, vertically, it's always on the right side, I don't know, or like we switch it up.
Oh, no, I'm sorry. That's just my standard kind of example picture. My data could be temperatures in Alaska, correct?
Yeah, so I know what you.
So I could basically have data in every single coordinate, every single quadrant of this, yes? But I just normally put it here just, if I just wanna make an example. Is that okay, yes?
So then just copy what we found in the calculator
Do it again?
for that, for number two?
Yes? You don't have to do a damn thing in your calculator. You don't have to do anything in your calculator. Could you? Yeah. You could. If you made a bunch of data points that line on a line and you put them in the calculator, it would actually tell you R is 1, or in this case, -1. Yeah. Is that what you have? I'm not sure if that's what you have. To answer number 2, you don't have to do anything in the calculator. Number 2 is a conceptual problem. Are those data points that they come from somewhere? No, it just made an example of what it would look like. Now here's a little tricky side note. If I graph data and it makes a straight line, does that always mean perfect correlation? No. So here's why. You all agree, I'm looking at a tree right now. You don't have to agree because I could be lying to you, but I am. I'm looking at a tree right now, yes? That tree is a certain height, you with me? Alright, you ready? Alright, what happens to the height of the tree if I jump this much? Did the tree grow? Alright, be really, really slow. What if I jump more? Did the tree grow? Or shrink? So, if I plot how high I jump versus the height of the tree, won't I get data that looks like that? That's a perfect line, correct? But that is perfectly not correlation, because as one data point changed, did the other one give a shit? So you gotta be really, really careful. And the same thing with a straight line up. That would mean the other way. That one variable changed and the other one didn't care. The whole idea of correlation is as one variable changes, what does the other variable do? So if I have a diagonal line, now as one variable changes, the other one is also changing. That's a correlation. If I have one variable changing and the other one doesn't give a shit, that's gonna make of course it's gonna make a straight line. But it's not gonna mean correlation. Yes? That's a little side note, but I just want to put that out there because it's not a complete picture without that.
Wait, so, but that means that always, right? That's always the truth, because.
If I ever get a horizontal line or a vertical line, that is no correlation.
Okay, always.
Always.
Okay, thank you.
You're welcome. And just a real quick, don't even do this. Just watch. Just watch as Jeff pushes the wrong buttons. There we go. Watch as Jeff forgets where he puts his glasses. Way the hell over there. Okay. Real quick, don't even do this. So here's me jumping, and here's the height of the tree. Yes?
Yeah.
And if I go stat, calc, linreg, blah, 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 blah. Oh, look, it gave up. Yeah. It's like, nah, that doesn't even, no.
Doesn't make sense to me.
I was curious, I couldn't remember if it gave a 0 or what it did, but it just says, nope. You guys understand? Okay, I'm not gonna give you a problem like this. I'm not gonna freak you out, but just to make a complete picture. Also, did you guys notice when you went to the, do you see below 4 linear regression? Do you see this is quadratic regression? So if I have, do you agree with me that air conditioner usage is kind of parabolic?
Yeah.
A lot when it's cold, not very much when it's nice, a lot when it's hot, yes? So if I had data, it would actually follow a parabola. It might have no linear correlation, but it does have correlation, it's just a different shape. So you get quadratic, you get cubic, you get quartic, you get natural log. We're just gonna do linear, okay? Depending on where you go from here, you could do some of the other ones. Okay. Sorry, I'm just throwing a lot of stuff at you that you don't have to worry about, and I'm sorry about it. So let's get into the last new idea for the whole semester. It's the last new idea. This one is tricky, and I want to start with a reminder. Let's kind of go back over some of the main stuff we've learned this semester. Can you all draw for me our old friend, the normal distribution? Can you just draw a normal distribution? Our old friend. Normal distribution. Some of you guys are freaking out, but just a normal distribution, right? Yes? We totally are. We have declared bankruptcy.
So this is all for chapter 12, right?
Huh?
This is all for chapter 12?
That's chapter 12, yes.
And then we're moving to chapter
Now we're going to chapter 11, because we're just like that. Okay. You guys feel okay about 12? With some practice, it should be relatively good. Okay. And if anything goes wrong with your calculator on a test day or whatever, because they, just let me know. Is that
Say
simple?
clear it.
Okay.
Motion.
What's that? Sorry? Yes?
Chapter 11.
We are, but I haven't even discussed how to do it yet. It's the same paper, I just put it on that same paper. Okay. So let me draw this. Here's my normal curve. Let's see how nice I make it. Ooh! Okay, sorry. Anything to do with drawing or writing, if I do it well, it's a big deal. How many, guys, how many formulas are associated with values that fall into this picture? Can you tell me one of them? Usually, sorry.
I know.
Give this man a number.
The T-score,
Okay, T-scores.
X
Z
scores.
scores.
Z-scores.
Wow.
Standard deviation.
That was like.
It's okay. No, it's okay. It's just the heart of the course. That's all.
It goes in and it goes out.
So T-score. Let's focus on Z-scores. Z-scores fall into this. Now, we call it a normal distribution. Z-scores fall into this distribution. I am talking slowly because I want to show you the actual formula, because I don't think I did. I might have. The actual form. You ready? I can make my calculator draw this.
Are we doing
No. I mean, you could. We could if you want to. Let me know if you want to. There's the formula. That is the formula that if you plugged it in your calculator, let's do it because it's kind of nifty. Can you guys all see it? You don't have to write this down. You never have to look at this formula again, except for when I'm going to put it in the calculator. You ready? Is everybody with me? That is the formula that makes this shape. Yes? Okay. So this shape exists, and then when I calculate certain values, they fall into this shape. Does that make sense? Yeah. So we had a lot of different formulations for the z-score, correct? So before I graph this out, we had this was our first foray into it, and then we had this a little bit later. Yes? And then we had this one, which is just a slight change on this guy. And then we even had this one, which we didn't use much altogether, but some of you guys might have done a little bit with. This was if you have two samples. Don't worry about this one too. This is chapter 10. But look at all these different, in some cases, very different formulas and they all end up giving me a value that lies in here in certain situations. Are you guys all with me? For example, if n is greater than 30, or if n, p, and q are both at least 5, then they kind of fall in that picture. Yes?
Yeah.
So the picture exists, and then I have formulas that happen to end up with values that fall into that picture. And why is that good? Because I know everything about that picture. I know exactly, we got a whole chart that shows the percentages. So if I know something falls into that picture, I can do all kinds of probability questions. Yes? Okay. What we're about to do, before I go into what we're doing today, let's graph an example. Can somebody give me any mean you want? Give me a value of the mean. This, 32, kick ass. Somebody give me a standard deviation, maybe not too big.
1.34.
Do it again.
1.34.
1.34, okay. Now everybody just stay calm. as Jeff takes for goddamn ever to plug this stuff in. Hold on. Sorry. Sorry. This is not at all obvious, by the way, so don't freak out if you're like, why is it like that? And it's not obvious at all. Let's see if Jeff can do this correctly. That would be so awesome. I can do it. X minus, what was it, 32? Jeff, you already screwed up. It's all right. It's all right. You can save it. There you go, buddy. Please don't try to do this yourself. Hold on. Divided by, what was it? 1.34. All of that squared. Let me see if I did all that right. Oh, God.
And you put 0.6.
I did. What did I do? Oh, yeah, I did. On purpose. Okay. I appreciate that, though. Oh, it's mean is 32. Damn it. I can only see up to 10 right now. So just watch. I'm going to change my window so I can see far enough over to see 32. Is that cool? So I'm going to go from like 20 to 60. And I'm going to also change this to -3 to 3, I think. Oh no! Okay, let me change. Sorry, I forgot. Of course, it's not. It's going to be very much smaller than this. -1 to 1. That might be better. And then let's just go to 50. Okay, this might be a little better. Let's see. There he is. There he is. Look at him. He's cute. Let me zoom in on him a little bit with my favorite thing in the world. Enhance. This is the CSI enhance. Yes.
Yeah, I know.
Enhance. What are you guys talking about? What happened? What's that? No.
Like I do.
Just like remember episode South Park, Osama bin Laden episode.
The Osama bin Laden episode?
South Park, yeah. Marvin, he's treated like Bugs Bunny.
Oh god, yeah. Okay. Oh.
Phrasing. The
Well,
way you were saying it, phrasing.
oh, well that's an Archer mix-in.
Yeah.
Okay. What did I say, guys? Is there
You gotta zoom in. Look at that little guy. Look at him.
It
Oh,
was
God.
yeah.
Okay.
Yeah. And I didn't think anyone else thought it, but then I looked at her and she was looking at me, and I was like, oh gosh.
Well, look at him now. Oh my god, you guys. That I would never have guessed. All right. Moving on. Isn't that kind of cool? We got a normal distribution to show up on our calculators. And he's a cute little dude, poor little guy. All right. So, now, the point I want you to carry with you as I attempt to transition, all of these formulas relate to this picture, right? And we can construct this picture by taking a bunch of samples and plotting the z-scores, and I can actually construct this picture, yes? So what we're going to talk about today is a different picture that exists. And it has a different shape based on the degrees of freedom. So let me see, do I want to I should just show you a computer generated picture that's probably better than what I could draw. Well, I mean, I could draw the basic one, but I could draw, yeah, I don't know where it is. Degrees of freedom equals 1. What does that mean? How big of a sample would I have? 2. Okay. So my sample size is 2. It actually looks like this. And to be really, all right, I'm going to give you kind of a full mathematical picture here just for a moment. Not a full one, but more than I normally would. If you take the normal distribution and you fold it on itself and multiply the values you get, you'll get that picture. So this goes up, this is 0.5 here, so 0.5 times 0.5, 0.25 here, and then it goes down forever as these. If you fold this on itself and you multiply the values, you'll end up with that picture. which is one reason why, and the reason I really want to talk about this. So if I fold these and multiply, don't I end up with like z squared? Is that cool? I'm like multiplying z times itself. So this is called, now this letter doesn't make sense, but this is the Greek letter chi. I know it looks like an X, but see how it's all curvy? So it's not X, it's chi. And it's got a square on it. You can never remove that square. Do not square root it. It don't give a shit, because that's a part of its notation. And the reason it's a part of its notation is fundamentally, it's the square of a relative z-score chart, z-score distribution. How much do you have to actually understand about everything? Do you ever have to apply what I just said? Never. But I want you to see why it's got a square on it. We're almost never going to use this picture because is a sample of size 2 good enough? The minute you get a sample more than 2, the picture will pretty much always look like this. Yes?
So the picture where the black one, that means it's.
So which one? Which picture?
The second one?
Second one?
So basically that's the normal distribution, and if you fold it, that means it's already like the other one.
Yeah, so if you fold it, and what I mean by folding it is as you fold it, whatever the z-scores that line up, you multiply them together. So that's why I said it's like a z-squared. And that explains why there's a square on the notation we use. That's the square on the chi. That is a symbol by itself. One symbol, chi-squared. So this is a chi-squared distribution. I sometimes call it a Jabba the Hutt distribution. Because it just, I don't know, any other Star Wars fans, it's got this big, it's got a big tail. It's freaking Jabba the Hutt. What do you want? Is this a symmetric distribution? Yes, you do. Look at it. Is it symmetric? Is the normal distribution symmetric?
Yes.
Okay, what does symmetric mean? Is a parabola symmetric? Why?
Same on both sides.
Because if you fold it, it folds on top of itself, yes? It's got a mirror in the middle. Is the normal distribution symmetric? Yes, it's got a mirror in the middle. Is this symmetric? No, thank you. Okay, so it's not symmetric. Also, considering where it came from, just look at the normal distribution. What value is this? What z-score is this? Right here?
0.
Yes. So what chi-squared is this? 0, because that's where it came from, yes? So what's the lowest chi-square can be?
0.
And then it goes theoretically forever up.
Also, no negatives.
No negatives. Again, which is another reason why it's nice that the symbol has a square on it. It will remind you it can't be negative. Okay, so that's kind of nice. Some students don't like the square, gets them confused. Just say that's just the notation. That's what it is, and it reminds you of a couple of important things. It comes from squaring z-scores, and it can't be 0 or negative. I mean, it can't be negative.
So chi
Say again. Cannot, yes. And that makes sense because it's squared. Okay. The same way that multiple formulas fall into this guy here, multiple formulas also fall into this guy here. I'm going to start with the one that we're actually going to end up not using. But it is the fundamental formula that actually kind of like explains this shape. I love this. This is the last new idea. So we're going to make, we got today, and then we got after the quiz next time to do this. We're going to be okay. It's kind of like one of my favorite comedians. He's always like, every now and then he says, we're having a good time. He's like, you know what I'm talking about, Dusty Slay? We're having a good time. I just wanted to tell you, just in case, we're having a good time.
That sounds great.
This is making sense, everybody. Okay. Do you guys? Okay, I want to back up a second. Multiple formulas lead to values that land in this picture.
What's that one right there?
What,
Is that PA?
down here, this is PQ.
PQ.
I just wrote it real quick because it's just one of the formulas that gave us a z-score that fall into a normal distribution. This shape has multiple formulas that fall into it.
I didn't know that.
Say again?
I suppose it has a face.
Oh, yes. That's when I called it Jabba the Hutt. Okay. I never expected this lesson to be difficult to do. Okay. In terms of just getting it out there. Okay. So here's the one that we're not. Okay, let me just write it down. Does anything look familiar in this? A lot should look very familiar in this, yes? The formula itself doesn't immediately make sense. What's n minus 1? Variance of freedom. What's s squared?
Standard deviation, or
Sample
Standard deviation.
variance.
Okay.
And what's sigma? Oh, hey. What's sigma squared?
Standard deviation.
Population
Standard
variance.
What is variance?
Variance is before you take a square root. Look at your test 1. Look at problem number 2.
Right.
So variance was before we took a square root. Yes? Okay. Let me stop for a minute. Let's compare this to the z-score formula, the basic z-score formula. Do you see how the z-score formula takes a data point and compares it to the population, right? So it takes something from our sample and compares it to something from our population, yes? Something from our sample compares it to something from our population, yes? Now, that does it through subtraction, this does it through division. But it's still kind of the same idea. I want to compare these two. When I take a sample, I would put a lot of money on our sample standard deviation being different from this, yes? But shouldn't it be close if I took a good random sample? So all the values in here correspond to S's that are close to sigma. Let me stop for a minute. What's up? When S is equal to sigma, don't these cancel? And then you get n minus 1. So the height of this is actually kind of related to n minus 1. I'm going to have a lot of samples that have a standard deviation of 0. Could I have a sample with a standard deviation of 0? Totally. So that's why I don't have much down here. I don't have much down here, right? But I do have some stuff. Sorry, I'm going to stop for a second. You guys kind of with me? Yeah. And then it gets more in the middle. Just like this, most of our samples should show up close to the mean. Same kind of idea. Okay. So it's a very different looking distribution, but not that different. It's just been pulled. Does anyone know the official name for this kind of distribution? Skewed.
Yes.
Skewed. Which way? Skewed which way?
Right.
Right. Yes. Okay. Somebody grabbed Jabba's. That's why he's upset. Let go of my tail. Oh, oh, oh. Okay. Now, so this, if I calculated all of these for every sample I could take and plotted them, it would create this picture. Okay, so this is a good one. This one is used to do confidence intervals for standard deviations. This one is used to do hypothesis tests for standard deviations. So the job of chi-square is very similar to the job of z. How far away did you get from something expected or something you're testing? Yes? Maybe? Okay, maybe. The formula I'm going to focus on is very different from this, but so are like these two. These are very different, yes? But they both relate to the same variable, z, yes? So I have one equation that's useful in a few different situations that leads to this chi-square value. Here's the, okay, let's do it this way. I'm not going to just give you the formula. I want to show you where it comes from. So. Yeah. So that formula, we're not going to see, besides what I just talked about.
I like this formula because it's the most basic chi-square formula. We just don't have all the time in the world to actually, I'm not gonna make us suddenly do hypothesis tests with standard deviations all of a sudden. You guys might rebel. You guys might mutiny if I make you do another kind of hypothesis test. Although, I don't know, maybe, do you wanna do it? Okay, all right, this is what I thought. But this formula is really good conceptually because it has kind of the same information. Sample, population. Sample, population. Yes? It's comparing those values, just in a different way, but at least it's comparing those values. So, let's say that maybe it's best. No, okay. What if I'm trying to figure out what's the best way to do this. Yeah, let's do the one from what I gave you just now. I think that's best instead of me trying to make something up on the fly. Turn to this side of your handout. This is a completed problem, which is fine. Read through the problem. We take a bag of M&Ms and blah, blah, blah. Say again?
It kind of sounds like chapter 1.
Oh, okay.
This sample, and then we have to make this sample.
Yeah. It feels like those tables we did back in chapter 2, but it's all right. If I have 42 total M&Ms in a bag, let's say, right? And my claim is that the colors of M&Ms are uniformly distributed in the population of bags of M&Ms. Are you with me? Which means any sample I take doesn't have to be uniform. So I'm not going to make a complete hypothesis test out of this either. Does it make sense? If I get a bag of M&Ms and they're not exactly 7 each, is that by itself evidence that the entire population of M&Ms are not uniformly distributed? No. That's just one sample of M&Ms, correct? Yes. So if I have less blues, maybe somebody next to me has more. So kind of like overall, it does come out to be uniform. Okay. So I got a bag of M&Ms, and I observed these 5 browns, 6 yellows, 5 reds, blah blah, yibba blah. Yes? Okay. Why is there 7 there? So if I have 42 M&Ms and 6 colors, yes? If I think it's uniformly distributed, how much of each color should there be? 7. Yeah, 42 divided by 6 categories. I would expect each category to get 7. Now, does everything I just said make sense? Including the word expect, yes? Yes. Just want to highlight that word because it's a huge thing for this process. I have an expectation and then I go do an observation and I see how close that is to what I expected. What I love about this formula is it has exactly those words in it. So it's actually kind of really close to the way I would say it. We observed this. This is what we actually saw. This lines up with our claim. We claim that they're uniformly distributed, which means they all should have the same number of M&Ms. Yes? Do you all agree with me that my sample is definitely, for the most part, different from that expectation? Yes. Green, so like I'm doing, I'm supposed to, whatever. You guys know? Okay. So, look at me. Sorry. Doesn't it make immediate sense, based on what I kind of just said, that the first level of analyzing this is just to see what the difference is between what I expected and what I saw? So, one reason I don't like what I'm doing, I'll be okay, is I kind of wanted to do this from scratch, but this is okay. So, if I just did observed minus expected, wouldn't some of these be negative? Yeah. And do you remember what we did when we tried to figure out the standard deviation? We had to square them for the same reason. Yes. So they didn't always add it to be 0 or something. So I find the difference, I find this is a beautiful problem. It makes
a weird amount of sense. I have an expectation, I make observations, I get the difference between those. That makes immediate sense. How different were they? How was the observations I made different from what I expected to happen? I square them for the exact same reason we squared a long time ago. Now here's the kicker. Let's say is everybody good with everything so far? Or decently good? There's more shit to talk about, so let me just get there. Reset a little bit. Let's say I have a lemonade stand. And I expect to make 20 bucks. And I make 50 bucks. That's a difference of 30 bucks, right? In that case, is that like substantial? You can do it. I expected to make 20, I made 50. That's substantial, correct? What if I have a business and I expect that business to make $20 billion? And it makes $20 billion, 20 billion and 30.
No.
That's still a difference of 30, correct? Is that a substantial difference?
No.
Okay. So everybody just get a feel for that? So of course, it makes complete freaking sense. Not only do I want to know how far off my expectation was, I want to know relative to what the expectation was. If I expect to make $20, then a $30 difference is huge. If I expect to make $2 billion, a $30 difference is nothing. Okay, good, maybe. I want every step of this to just make sense. So I know this is the absolute difference, but I want it to be a relative difference. How big was the difference relative to how much I expected in the first place? Is everybody kind of with me? Okay, beautiful. Because this could be very tricky, but to me, it's really nice how it goes together. What's really interesting, and just to remind you guys, if I do this shit, I get a Z-score. Magic. If I do this shit, I get a Z-score. Magic. And it falls in there. If I do this, if I add up all my relative squared differences, it becomes a chi-square score. It falls into the distribution. It's analogous. Those two situations are analogous. We've discovered that the distribution of all these scores ends up looking like Java 11. Yes? So if I do that, so are you guys seeing, like, 5 minus 7 is negative 2 squared is 4. 4 divided by 7 is this. Blah, 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 and then blah, 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 blah. And then I add this shit up, and I get 3.143. Now, is that cool light cell? The 11.07, now we gotta talk about that. What would the, once you get if you do a hypothesis test and you get a Z-star, what do you compare that to? What's the step before you get your Z-star? What do you set up? We have to figure out if it's normal. So it's normal, blah, blah, blah. What do you set up to be able to tell if you found enough evidence? Rejection region, yes? And how do I get the number for the rejection region from the Z-score chart? Or from the T-score that also has Z-scores? You guys with me? Yeah. We just calculated a chi-square score, correct? Don't I have to look into a chi-square chart and get its number so I can compare? If only we had a chi-square chart. This is your last blue chart. Hopefully I didn't make anybody hate the color blue now. Okay. By the way, I am so tired from this week. I'm really hoping I'm not, that I'm making sense. This week has been crazy. All right. This chart is evil. The Z-score chart, when I look it up, it tells me the area to the left.
Also, it's like you want
What's this one to? To the right. Okay. Do you see what looks very familiar though? I mean, here's degrees of freedom. So, but this is the first difference. Degrees of freedom for, you gotta love it. This is not my phrase. This is the actual name. It's a goodness of fit. So in this case, what am I trying to see? If M&Ms fit a uniform distribution. Good. Yes. So we call it goodness of fit because stats people are very creative. Fit good, goodness of fit. The degrees of freedom for this kind of problem is not n minus 1. How many categories are there for this problem? 6. Yes? Well, 6 colors. So the degrees of freedom will be the number of categories minus 1. That is only for a goodness of fit test. So on one level that feels familiar, but on the other level, don't do 42 minus 1. I understand if you do, but you got to remind yourself. Now watch, this is hilarious. So that's obviously, let me think, 5. Watch the formula. Ready for the formula? So remember, 6 was the number of categories, correct? So of course it's k minus 1. Because that's people were super creative and we spell real good. We talk good too. Huh? K is the variable to make you aware that it's not n, and it's just kind of funny that it represents the number of categories. How you guys doing? It's just a variable they chose, but it's funny they chose K. It's kind of like, so you're misspelling category 5. So, the degrees of freedom is 5. What's my level of significance? Yes, and the beautiful thing about this chart, for a goodness of fit test, I'm going to look exactly where it says 0.05, so I'm not going to worry about this side. This side would be if I'm doing confidence intervals. So what do you get for 0.05? What's the degrees of freedom? 5. 0.055, you get?
11.07.
Yes, 11.071. Now, I love you guys. Real quick, somebody help me out. I'm going to make all this come together now, right? So you can find that that's exactly like your rejection region, so I shaded it in. So if I got into that region, I would reject that it follows a uniform distribution. That would be evidence it doesn't. So if M&M was on their commercials, we have a uniform distribution. They don't, but if they don't like that, that's a appropriate reaction. We would say, actually, we did the study, and you are full of shit. That's basically what the study said. Obviously, we didn't make it there, so we can't say that kind of shit. If our observations were exactly what we expected, you with me? What would that look like in the table? Everything under observed would be 7. What would all my O minus E be then? 0. What would my chi-squared be? 0. This means our sample perfectly follows the expectation, correct? I need this to make sense. 0 would mean that our sample perfectly follows the expectation. Dumb question for you. Is that evidence that it doesn't follow the distribution of the population? No, obviously not. So, just like with hypothesis, not only do I have to be different from that, I have to be different enough. Because any sample I take has variability. You with me? So just a sample being different is not evidence the whole population is different. This number is where evidence starts, and then I calculated how far did I make it. So it's not going to have all the steps of a hypothesis test. It's just going to have the best parts. Here's where evidence starts. We didn't make it. So did we just reject the claim that it's uniformly distributed? No, we failed. So we haven't shown that they're not uniformly distributed. We didn't make it. So that should feel very familiar, but with a lot less of the steps. Please let that be okay. Yes?
And then you said the zero would be what? If it was zero?
Yeah, if I got chi-square, the only way I can get chi-square 0 is if all my observations were exactly what I expected. Then their differences would be 0, yes. So that's why not only do I have to be far away from the situation where it lines up perfectly, I gotta be so far away from it that it's evidence that it doesn't line up at all. Maybe. So you guys have that gaze, like, please just let this semester stop. I want to do the next one with you, because there's only 2 types of problems that can show up in this. One is uniform distribution. The other one is a follows an established distribution. So look at number 2 here.
Read through that real quick.
Yes. Yes. Actually, yes, that's a good point. I'm going to do something you're not used to, by the way, for a quiz or a test. I'm going to put all of these, at the top of your chart. Because you don't have much time to live with this. Do you all agree? I'm not quite shoving it in here at the end. Kind of shoving it in. So I'm going to put those on your chart. Yes? Then you just have to fill it all in and do it. So if you're going into any psychology or whatever, this is huge. If you go into, well, a lot of different things, chi-square becomes very important. It's how I move towards analyzing more than 2 variables at a time. It opens the door to analyzing multivariables. But don't worry about it. I'm sorry. So everybody's read through this, yes? Yeah. Do you see how my claim is not that they follow a uniform distribution. My claim is that they do this. So if I want to fill in, now here I was very nice. Now don't get excited. I'm not going to put this shit down. But do you see how I got that? If I take 500 people, if they follow that distribution, how many people do I expect to have less than 130? Less or less? Well, what percentage do I expect? 20%. And I had 500 total people. So how many do I expect? 100. 20% of 500, yeah. So either the claim is it's uniform. Then you just take the total number divided by how many categories. That kind of like puts them all into all the categories. Or I give you percentages that it's supposed to follow, and then you calculate each one. So keep going. Less than 130, we expect 100. Jeff. I'm still kind of getting used to actually needing glasses, so I keep forgetting them everywhere. What's 30% of 500? 150. 35%.
175.
Beautiful. 15%. I think it's 75, yeah? Yay! One thing you can do for yourself is to add all these up. What should they add up to be?
500.
And thank God they add up to be 500. Yay! Now what goes here? Yeah, I observe 111 below 130, 184 between, why did I say 140? That's a typo, guys, I'm sorry. I should say between 130. Thank you. And then 137, and then the rest. Look at me being evil. 68. Okay. Not too evil. You guys are like, whatever, Jeff.
We added.
Yeah, totally. Add them up and subtract from 500. Yes. So I have to always tell you the observations, because you're not actually looking at these people, I'm gonna tell you. You're gonna calculate what you expect. Either it's uniform and you divide and they're all the same number, or you do percentages of the total number, yes? That's the only two things that can happen. And now you just do what the thing says. And if you notice, you could put this in your calculator and do like we did before. L1 would be observed, L2 would be expected, L3 would be L1 minus L2 whole thing squared, yes?
Yep.
So I'll do that, and you can do it either way you want to. Oh, there's my little dude. Where is it? Stat edit. You guys are funny. By the way, just in case you didn't know this, watch what I could do. I could put in here 0.35 times 500, and it'll do it and put the number in there. So you can do math in the middle of a table. Damn! I want L3 to be L1 minus L2 squared. And you don't have to do it the way I'm doing it, especially because I just did something really weird. So I'm getting these numbers. Is that what you guys are getting? I liked 121, 1156, 1444, 49. And then I want L4 to be L3 divided by L2. I want it to be these guys divided by expected. Shit, I didn't want to do, okay. So I'm getting 1.21, 7.7067, 8.2514, and 0.6533.
Okay, wait, how did you do that?
Do
What
which
did
part?
you divide by?
Oh, so for example, if you're just doing it step by step, you would take O minus E squared divided by expected. So 121 divided by 100, bam.
That's right.
1156 divided by 150, bam. Yes.
Why do you want to clean this crap?
Oh, because you have this set, go to mode. And, okay, why is it? That's weird. Wait a minute. It looks like it, wait, let me see. Blah, blah. Oh. Neato. Okay, so, let me see if that'll make it better. No. That doesn't make any sense. Why is it doing that? Wait a minute, let me change it and then change it back, change this and change it back. Why is it, oh, I'm not sure, wait a minute, so, alright, did you, wait a minute. Okay, alright. I think it's good now. I think it just didn't oh, that's right, because a table doesn't update when you make a change. So I had to go in and make it recalculate. Yeah. How do I say, so like this? So put like your observed, your expected. L3 is going to be parenthesis observed L1 minus expected L2 squared. Huh? What? What is your L1? What's in your L1 in your calculator? Well, what's in your calculator? Are you doing it in the table? What's right here? Do you have 111 right here? Okay, and what's right here? 100, okay. And up here you put, let's do it together. L1 minus L2 squared, yes? Is it good? I think you put L1 minus L1, because then that would come out to be 0. Okay. How's everybody doing? So now to get what I could call chi squared star, but that's just kind of silly.
I add these up. Did anybody add these up yet? Oh, I always forget. Big ass E. There. So just add these numbers up, and then let me know what you get. 17.82. I'll take it. Sounds about right. Now, that is where our sample ended up. So we're kind of doing this backwards from a regular hypothesis test, but it just kind of makes sense to attack the chart first. Now I want to set up my rejection region and see if we found enough evidence. What's going to help me do that? What did I tell us that's going to help us look in the right place?
17.82. Oh, your degrees of freedom.
Yeah, degrees of freedom. What's the degrees of freedom?
A minus 1.
No. 3, K minus 1.
Okay.
So.
That's right. And on the Sesame Street I watched, K was for categories. So 3, because it's 4 categories minus 1. Yes.
I'm sorry. Is
Yeah.
all of that added up right?
Yeah, this guy,
So-
sigma,
Sig-
is just adding these up. Yeah.
Okay, and then we do the, let me plug it in.
No.
Oh.
Well, you add these up,
Yeah.
and that's how you get 17.82. Yep. Just add these up.
We don't put it, just add it.
Just add them up. Yep.
So guys, degrees of freedom is 3. Alpha is 0.01. What do you get for the critical value?
11.345.
Beautiful. So alpha is 0.01. Degree of freedom is 3. 11.345. So if I graph my little Jabba the Hutt, 11.345, right? And we got to 17. Look at us go. So what the hell did we just do?
17.82.
We have not found sufficient.
Oh, did we not?
Oh, we found sufficient
We
evidence
blew this shit away.
to reject.
Yeah, we can reject that these people in this area follow the general cholesterol pattern. Now, is that okay? We're always saying, does this group follow this pattern? If we get into the rejection region, we can say no. We don't, we can't say no.
So we have found sufficient evidence.
No, you don't have to do it. Just say they don't follow the general pattern. I'm gonna be a lot more lax about the interpretation here, yes. Now, real quick, just to add a little more on this. Is it better to have low cholesterol?
Yes.
Good. We've shown evidence that they do not follow the general population, correct? Don't they have more people with less cholesterol?
Yeah.
And don't they have less people with more cholesterol than what would be expected, correct?
Yes.
So I can go a step further because we observed that too, and I can say not only did we show evidence that they're different, but we showed evidence that they are better. They eat a certain diet. So then I would go, what the shit are these people eating? So this is kind of like in the 80s, I think it was, and you guys are like, oh, well, that's ancient times. We discovered that people in the Mediterranean had low cholesterol, they had lower body fat, they had all this stuff. So instead of thinking to ourselves, because we're Americans, they were Americans, instead of thinking, oh, it's because they walk everywhere, they don't, they actually value extra wealth. No, we went, oh, it's the olive oil.
It's
And then you had people just shove it out. They would have what they would normally have anyway, and they just poured out olive oil on it. Oh, doing the Mediterranean diet. You can look it up. Google that shit.
It was.
Mediterranean diet. Steven, you lived through it a little bit?
Man, it was 91, so kind of.
You know what I mean?
I remember olive oil became so
Olive oil
popular.
was the thing. It was the shit. And then eventually people are like,
Everybody threw out Alder Crisco, everybody threw out Alder stuff.
Yes. Now, olive oil is not bad. Don't get me wrong. Olive oil is not bad. But it doesn't suddenly make you skinny. It was other things that caused it. Yes. So this would be, I would go in with a deeper analysis to see, is it the water, is it the air, is it the lifestyle, is it the diet? I don't know. Yes. Alpha was 0.01. Degrees of freedom is 3.
let's say that's enough. Next time, we'll do more examples of this after the quiz. If you didn't hear earlier, there's a quiz on linear regression. Tuesday, next time.